Well, good evening and welcome to Codebase Alpha. It's the first time I've streamed this year. It's quite a time since the last stream, so I do apologise for that. But a certain amount of real life is going on at the moment, and it's not over yet. So um, I do apologise for not being around. Um, okay, so today we're going to look at progress on the Z80 emulation project and see what we can see with. Oh, thank you very much for whatever that was. I didn't quite see what it was. My alert's not working on this particular screen, so thank you, whatever that was. I'll check in a second. Yes, we're going to look at the Z80 emulator. It's nearly done. We're very, very close to completing it. And we're going to try and look at the beginnings of an application with a Spectrum emulation. We're going to see how far we can get with that. I just want to examine how it runs a Spectrum ROM and see what we can see. There's no visuals yet, so that's kind of part of what we're going to be doing over the coming weeks and months, is to try and get a screen so we can see some output from the emulation and also interact with it through a keyboard. And the kind of end game is probably going to be at least to get us to be able to write basic programs on a Spectrum emulation. But we could take it further and maybe play games. But the problem with kind of game emulation is that you need very exact timing, and I'm not sure that I've got the timing of CPU functions actually down yet. That's another part of the emulation which we'll look at a later time. At the moment, I'm just really kind of worried about making sure that our CPU is as accurate as possible. So let's start off with some music. There we go, a bit of Relax Daily. That's what I need at the moment. And we'll just pop over to the code, shall we, and let's have a look what we can see. Okay, that was a subscription, so thank you very much. Unfortunately, I don't seem to have got a good alert on that one, so if that was you who subscribed in chat who subscribed, please do make yourself known. I do apologise for not noticing. Maybe I can see on the stream manager. No, we can't see anything about that, so that's very strange. Okay, so let's go and have a look at the code, as I say. Here we are. So this is the Z80 emulation code. So I'll have a quick run through of what we actually have done since the last time I streamed, because there's a fair amount of work happened since then. So let's have a look at the solution. Over here on the Z80 project itself, you can see what I've done is I've split up the what was the instructions partial class into a number of other partial classes, so that we've got commands and opcodes which are logically grouped together in their own partial class. I'll still get to do that with other parts of the instructions class. Copper Beardy, good to see you. Welcome to the stream. Good to, it's very good to see you. It feels a bit odd kind of to be streaming after such a long break, but we'll see how we get on. So I've done that kind of split and been through working on quite a few of the commands that were missing from our emulation. So there's a whole bunch of bit manipulations. So there's the bit set, reset, and test group, and so there's a whole bunch of them here. Actually, there's the partial class that contains this isn't very long. Luckily, there's a huge number of opcodes which are actually covered by these. I think we've got nearly 300 lines of code here. There's a couple of hundred opcodes that are covered by that. So that's given us some really good coverage of the instruction set of the Z80. We've also done some work with shift and rotate, so completed the shift and rotate. So this is where we shift to the left, shift to the right, or rotate left or right bit patterns. So that's as well. There's just over 1100 lines of code in there, so that's quite involved. And we've also done some work on I/O. So we've got some basic I/O commands here, in and out commands. And this is what I want to work on this evening. I want to do a few more of these commands. There are some kind of block I/O commands which would be useful to have. But the good thing about what we've got so far is it's actually good enough to run a Spectrum 48K ROM. I haven't come across any instructions that aren't already covered in what we've emulated so far. Now, the other thing that's kind of been working on is test coverage. So if I go over to our Test Explorer, you can see the company got 279 individual tests for the emulation. But actually, there's an awful lot more than that, because this final test here, pass all validation tests, if I show you that, this is running our Fuse tests, and Fuse is a Spectrum emulator, which is freely available on the internet. And with that emulation comes about 1,300 plus individual validation tests. And what I did in a previous stream is I actually implemented those tests. And if I run our tests now, we can run this particular test. That's probably the best thing to do. Let's run it in debug mode, so it'll get a little catch on this this breakpoint here. Excuse me. So let's wait for those to run. Luckily, it doesn't take that long to run, so we can just ignore that. You can see we've got no failing tests. We've got 1,231 passing tests. Add to that the 278 individual tests that I wrote as part of the initial part of the project. We've got, heading towards 1,500 tests, and say we've got unimplemented tests. We've got 125 more tests. So those tests are there, and they are so good that I no longer feel the need to write my own unit tests. These Fuse tests are really, really kind of solid, and will help us to get our code right, at least as far as the emulation is concerned. In terms of the input-output tests, we've had to kind of bodge that slightly, because we've got no way of really interacting with peripheral devices in a test. And so if I go over to the in the tests, we have a implementation of the iBus interface, which is our basic bus. You can find that here's basic bus, and for the read peripheral and write peripheral, we're simply returning the value of the port shifted 8 bits. So it's going to be whatever port we write to, we're going to write back a 0, basically, what this does, and we kind of read back the data here. So we're not actually performing actual reads and writes to peripheral devices. However, that's the easy bit in a test. Right, we know that if we write to a memory location, it will write that data there, whatever form that peripheral or memory location actually takes. And if we read from it, we know from our read and write methods that we can read from emulated memory. And so it's not actually important that we read actual values from these calls. It's all the other associated checks. So checking that the registers are updated correctly, that this thing called mem pointer, which is this kind of pseudo register, is also updated. Oh, Rambling Geek, welcome to the stream. Thank you so much for the subscription. So let's have some hype. We did get a subscription earlier, but I didn't manage to catch who that was. So have some hyperspatial hype with Alf there. This is one of our shaders. We've kind of developed these shaders on stream. Okay, so that's the kind of the fake I/O that we've got going on. As I say, it's not actually important. It doesn't really conduct any I/O for the tests. It's all faked anyway. Okay, what else have we done? Well, apart from spending quite a lot of time writing lots of operations, I've also looked at my debugger. So with the debugger, we've also got an implementation of the basic bus. In this case, what we're doing with the read and write peripherals is we always return 0 from a read peripheral, but we actually write out to the console what we're trying to pull in from the peripheral, what we're trying to read from the peripheral, and down here, when we write to peripheral, we simply write out what we would have written to the peripheral. So that's how that covers that. We've also added a couple of new elements to the IBUS interface. There's the interrupt and the non-maskable interrupt, and this data list here. And I'll talk about that in a short while. So let's go and have. In fact, we'll do that now because these are quite important. So when you've got a CPU, you probably, I don't know if people have been, I don't know how often people actually dig into what their PC actually does under the covers these days. Back in the day, we kind of learned all about what was going on. And one of the things that in early PCs that you learned about quite quickly was interrupt requests. And these were from peripheral devices, and often you had problems implementing peripheral devices, especially expansion cards for your computer, because they both, you might buy two expansion cards and they would use the same interrupt, and you'd have to kind of change jumpers on the card to try and make them use different interrupts, interrupt 14, interrupt 15, whatever. And sometimes you couldn't do that, so you actually couldn't have both cards in the system at the same time. Well, this idea of interrupt is where a peripheral device can say to the CPU, stop what you're doing and service my request. So it says, stop running your current program, push all your data off onto the stack, and now run my little bit of code, which is usually a very short piece of code, and then it returns from that interrupt and the CPU continues what it was doing. There's two types of interrupt on the Z80. There's a plain interrupt. We could call it the maskable interrupt. So with a plain interrupt like this, the programmer can say, actually, I don't want you, CPU, don't want you to service these maskable interrupts for a short period. So I might say, I'm coming into a pretty critical part of my program. Do not service an interrupt while you're running this bit of code. But it's important that you do allow interrupts, of course, because a lot of things like polling the keyboard rely on the interrupts. The non-maskable interrupt is the concept that this is an interrupt that's so important that it's going to happen no matter what. You can't switch it off as a programmer. They're relatively rare. As far as I'm aware, they're not the kind of thing that happens all the time. Mostly it's going to be these maskable interrupts here. Let's go and have a look at the Z80 code, which is handling interrupts. So that's over here, and we'll take that. So you can see that when we're running a step or we're in run mode, we check, we run a step, we run one command, one opcode, and then immediately check for interrupts. We handle interrupts after each one. And whether we're in run, which is run forever, run to a particular operation, run as far as a NOP, for example, no operation, or the simple stepping mode, step, 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 step. The handle interrupts first checks for non-maskable. Was the interrupt non-maskable? And if it was, it handles it. And then, have I actually also got a maskable interrupt and handle that? We've got two different methods that do the interrupts. With the non-maskable interrupt is the simplest of the two, really. What it does, if the CPU is in a halted state, it unhalts it. It pushes all the program counters and all associated data onto the stack, and then it sets the program counter to a memory location 66 in page 0 of memory, and it executes that. Obviously, you've got to have written a routine which lives at location 66 on page 0 of memory. If there's not one there, you're going to crash. But usually the operating system will kind of generously call it. Will have a routine at that location. What we get to do is to actually cause that operation to take some time. At the moment it's instantaneous; it just runs through that code and then returns. But actually, it should take 17 clock cycles. A clock cycle on the Z80 is known as a T state. So it should take approximately 17 of those. And currently, as I was kind of alluded to earlier, we don't have a way of actually slowing our process down to realistic speeds. Remember, these Z80s, they can run at 4 megahertz or maybe even as high as 8 megahertz if you're lucky. But let's say 4 megahertz. And so we really need to, if we're going to have accurate kind of gameplay, which you could play, you need to slow it down so that so it actually takes the right amount of time to run a command. And we haven't done any of that yet. That's something if we want to play games. And currently I'm not working towards playing a game with the emulation. We're working towards doing some basic programming initially. And then we'll see how far we can get after that. There's plenty of obstacles ahead of us to get an emulation of a real machine, which actually shows us a screen and allows us to interact with a keyboard, let alone trying to play video games on it. So, but it's a kind of a goal for the future. The maskable interrupt is much more complicated because it starts off the same. It kind of pushes a lot of stuff onto the stack. But there's 3 modes of interrupts. Mode 0, which is probably the simplest. It's going to go to this up. It's going to go to a variety of interrupt locations. I think there's 8 different locations you can jump to, so you could have 8 different interrupt routines, and you set which routine it's going to go to. Once again, there's mode 1, which simply goes to a location 38 or 38. So that's very similar to a non-maskable interrupt. And then there's mode 2, which is a vectored interrupt. And what this is you can create a table of interrupt handling addresses, or the location of interrupt handlers in a table, and then by manipulating the interrupt register, you could actually say, okay, go to the 5th entry in the table, and that's the address of your handling routine, or go to the 10th entry in the table and run the interrupt routine that's at that location. So it's a very, very flexible way of creating interrupts. It simply runs whatever code is at that location. The difference with mode 0 here is that it doesn't run. It doesn't go to a specified location. It actually runs any command that you send into it. Currently, I've got it so it only responds to a reset command or a call, which is a subroutine call. Fuel Stable, welcome to the stream. Good to see you. Salute. So that's a different type of interrupt. So it's going to run a command. The difficulty with this one is we've got it set up to run a call or a reset, and those are simple. But in theory, it could any command that the Z80 can handle, and I've yet to decide how that's going to work. The Fuel Stable says, does ZD push the status flags, or do you need to handle it explicitly in the interrupt handler? You have to push and pull your registers yourself. What this will do, it will push the program counter, so it knows where it's got to go back to when you do a return from interrupt. But all the rest is down to the programmer to handle. There are a number of ways you can do it. We've got these shadow registers, so you can do a kind of a register exchange, but that's not really that dependable, because you don't know what code could be in an interrupt handler. So yeah, it's the safest thing is to push all of your registers onto the stack, and then to pop them again once you're ready to return. Same with disabling interrupts and re-enabling them. Normally, when you jump to your interrupt handler, you will disable interrupts, and you've got to remember to re-enable them at the end of the process. Obviously, if you forget, then you've actually switched off interrupts, and likely your computer will stop, because interrupts interrupts are normally required for human interaction with the machine, so for polling the keyboard or whatever. Certainly in the simpler CPUs, that's the case. I think it's the Amstrad CPC. It definitely uses interrupts. It interrupts 50 times a second to poll the keyboard. So I'm not sure exactly what the Spectrum does at the moment, but I'm probably not going to be using interrupts to handle keyboard input. I've got an idea, which is just a kind of a glimmer of an idea at the moment for that. So that's interrupts. Now the debugger, we're going to look at that. I got hold of a Spectrum 48 ROM, and that's this here. You can download these from the internet. They're kind of common. And I wanted to be able to load that ROM into my debugger and inspect the code. And yeah, I managed to get it to do that. But the problem was, there are large areas of the ROM which aren't program code. They're actually data. And of course, what my debugger was doing was interrupting everything as being a possible operation code, opcode. And some of them were illegal combinations because it's just data, ASCII characters or whatever. So I needed to update my disassembler for the debugger so that it will cope with that. So if you'll notice, there's a bit of ARM trivia. On ARM, the return address is saved and in the branch link register, so it's not pushed. If you have a simple routing, you don't need to push things to the stack. Because what you need to do is you move the branch link register back to the program counter. Yeah, so the ARM is a RISC architecture, isn't it? So it's kind of the opposite of. I mean, I guess the Z80 is not that complex, but it's got an awful lot of commands really for an 8-bit processor. I'm not sure how many opcodes a RISC architecture has, but yeah, it'd be interesting to know how many opcodes the ARM processor has, because there's this kind of this RISC was very popular at one point. It came in and people actually coined the term complex instruction set computer, which for things like the 8086 and that family, the 286. And at one point, the kind of RISC processors were the kind of the in thing, but it all kind of died away. But where the RISC is still going on is with the ARM processor, because it's a very low power consumption processor, so it's ideal for battery operated devices like your mobile phone. And I do think that maybe aren't Apple thinking of moving the ARM processor back into their Mac range? I did kind of think I heard that they were going to abandon the Intel processor and go to ARM chips, or at least something like that. So it's just interesting that RISC computing is making a comeback in the 21st century. But it was certainly a big thing in the late 80s. So it's rumoured, yeah. I thought I did hear it somewhere, but see, I'm a bit vague because not really heard anything since. I think there were 15 instructions in the original ARM. Good grief, that really is reduced instruction, isn't it? But each one does a very simple thing, takes one clock cycle, I imagine. You've been discussing switch to ARM on work in AWS fuel stuff. That's interesting. So that's how you get on with that. Okay, so let's. So what I did in order to kind of sort this problem out with the blocks of table data is I actually created a file format here where I could actually mark where the data in the ROM is actually located. So we've got key tables, we've got semitone tables, we've got the character set down here at the bottom, constants like pi, etc. defined here, and we've got these streams, input-output streams. So in order to find these out, I actually found a fantastic site, which is the Spectrum ROM Index. Now, Ramblin' Geek says, in case you didn't see, did you see you got the gRPC lib compiled and working, did you? So what? So do tell, Rambling Geek, because that was driving us nuts, wasn't it? What did you do to actually get that working? I'm so pleased that that's working for you, because it seemed to be a simple case of compiling it and dropping that compiled library into the right location. You compiled it on the Pi. Yeah. Copy it onto the Pi. Yeah. Into the build folder. So it built it and it transferred it to the right location on the Pi. Okay. Well, we should have thought that. We obviously did think of it in the end. So that's good. The fuel stable seats instruction, presuming the ARM has multiple extra options, such as the result can be barrel shifted or it's conditional. Right. Okay. Dressing modes are quite cool too. Yeah. So you ran .NET with no build. Stop it overwriting. So it was overwriting the library. I think that was the kind of conclusion we came to when I had to kind of leave the stream. Yeah. Okay. So this website is the Spectrum ROM index, and it's a disassembly of the Spectrum ROM, so we can use it to check our disassembly. But interesting, it has all the data blocks. So you can see these are the starting addressing of all the data, and these are the ones that I just showed you in my table. So for example, the start of the character set is at 3D00, and it actually tells you, it defines a byte, and it's actually a space or an exclamation mark or a double quotes or a hash, whatever, $. Okay, so it has the complete character set there. And what you'll see is the character set is made up, and this will be important in a little while. A character like this space is made up of 1, 2, 3, 4, 5, 6, 7, 8 bytes. And each byte, of course, has got 8 bits, and that acts as an 8x8 sprite. And so these are actually sprites. And you can see here with exclamation mark is that the first line is has nothing set, and then you've got ones down the middle, a 0 and a 1. That's actually a map of the of which pixels are background color and which pixels are the pen color. It doesn't actually say what color they are, the background of the pen are. That comes a bit later, but yeah, so that's how the data works. The fuel cell was saying you're looking at the current ARM is about 50 instructions. So that's, I mean the 6502's got 256 instructions, and that's an ancient kind of 8-bit processor. So 50 instructions it really is a vastly reduced instruction set. So excellent stuff. Yeah. Okay, so let's run up our debugger. So this is our WPF based debugger. It's still not complete. I haven't worked on the stack, playing the stack yet. But what I've done, I've simplified the interface. So there's now a step, a load. Load will load a hex file. We've also got a load ROM button there. So if I hit this, I can load the Spectrum 48K ROM, and it will load that in. There it is. And if we scan down, you can see loads of program code, and then eventually we will come to data. Well, actually, let's go and find out where that data is. So there's go back here. So at 0205 is the key table. 0205. You can see there it is. 0205. So this is the start of the data table, and we've got B, H. So these are the keys of the keyboard. B, the H, the Y, 6, 5, T, etc. And we've also got the space, of course. Oh well, I think that's actually probably non-printable characters, like some carriage return or something. Here's carriage return line feed. And we've got some characters which are just, these aren't actual keys on the keyboard. These will be special keys, 3/4 and these kind of things. has been interpreted by their current ASCII code. So that shows you how that kind of works. And if we go and skip to the start of this, the very first command we've got is di, disable interrupts, and then we've got ZOR, the accumulator, which is zeroing the accumulator. That's a shorthand for loading 0 into the accumulator. And then we've got we're loading register pair DE with the contents of the top of memory, FFFF. So let's quick look at the disassembly of this. Here's the start, and you can see the start is disable interrupts, exclusive or the accumulator, and load DE with the top of possible RAM, which is FFFF. So you can see that our disassembly is really reasonably accurate. And then we can next in byte 5 we're going to do a jump to start new routine. So here we're doing a jump to 11 CB. 11 CB will be the start of that new program routine, and that should all run. So that's quite cute. We can actually step through this. Stepping through it, it's not a very illuminating experience. What I do want to be able to do at some point is to be able to set breakpoints within this debugger, and then we can run to breakpoint and then step through particular routines that we're interested in. But we're not quite there yet. So that's that. What else have we got? Other than debugger, what I've also got is a sample project. So the sample project, if we look at the program, this is going to be used to kind of test out some of the ideas I've got for actually using this emulator for this emulated CPU for a Spectrum emulation. At the moment, what it does, it simply loads up the Spectrum 48K ROM file, and then it executes starting at location 0 in the ROM, and that's the piece of code we just saw: disable interrupts, exclusive or the register, the accumulator register, load top of memory, and then jump to the start routine. So we can actually run this. And what it does, it will run and it will print out what it's doing in terms of what operations it's running, and then if we press the escape key, it will stop, and it will dump out the memory locations 4000 hex to 5800 hex. And you might wonder why we want to dump out those locations. Well, I'll show you. So if we need to think about a memory map for the Spectrum computer. The Spectrum 48K, let's just look at what is at location. So at location $4000, and the dollar is simply, this is a hexadecimal number. So that area there, up until it's 57FF, this is the screen. So the screen's memory mapped, and this block of memory, remember we've only got 64K to play with here, it represents what is displayed on the screen. And there's a chip inside the Spectrum called the ULA, which is going to read this memory, this session memory here, 50 times a second, and it's going to update the display that you actually physically see. So this is a really important piece of memory, and what I do in my routine there is I dump out this range of memory so we can see what's in there. There's actually a bit more to the video RAM. Pure Snowball says, good old days when the screen is specific addresses. Yes, makes it quite easy to start hacking. Absolutely, and this is all the whole basis of lots and lots of fun you can have. Now 580, oops, 00, and it's 768 bytes. This next bit, the 768 bytes from 5800 is what's called attributes. I don't know why it's done that. Attributes. And whereas this range of memory here represents what is being displayed on the screen, this area describes the colour. So we're going to come to the encoding of the Visio memory very shortly. And I don't know about double buffering. You could possibly do it. I don't think the Spectrum did it though. I've yet to kind of work into delve into the depths of what the ULA actually did. It was quite a complicated little chip, I think. It did quite a lot of stuff. So this area here contains 768 bytes. Now, interestingly, 768. So a Spectrum 48K was 40 columns by 21 rows on the screen. And that's what you had to play with. And I think if we get our calculator up, and we say, well, that's 40 times 21 is 840, which is interesting because it's not the number I thought it would be, but never mind, we'll cross that bridge when we come to it. These describe the colours of the pixels, or the sprites. Okay, so actually, I think it's not 40, is it? It's 32. It's 32 columns. Of that. When I say 40, I've ordered a modern version of the Commodore 64, which is 40 column. It's actually 32 columns, and it's 24 rows. Okay, so I think if we do that calculation again, it didn't come out right. 32 times 34 is indeed 768. Okay, so this looks at the sprites that are on the screen, tells you what colours they are. So the way this is made up, single byte. So if we look at, say, I don't know, it's 7, 6, 5, 4, 3, 2, 1, and 0. We're not going to look at this area of memory this evening because I'm more excited about trying to figure out if we've got anything displayed on a screen, even though we can't see it. This is called the flash bit. So if this is set, then we're having a flashing character. This is called the bright bit. If this is set, then it's a particularly bright version of the colour. And we've got here, this is the paper. So this is the background of your sprite, and you can see you can have got 1, 2, 4, that's 7, 8 different colours. So it's 8 colours. And then you've got a bright version, so you've got 2 times 8. So you've got red and bright red, green and bright green, etc. And then the last 3 bits here, your pen. And your pen can also be obviously 2 times 8 different colours. So 8 basic colours, 2 versions of each colour, and they can be flashing. So that's how the kind of the attributes are going to work out. So if your snowball was asked about what about this area of memory here, because this is clearly a lot bigger than 768 bytes. So let's have a look at what the size of that area is. So let's get our calculator up again. Okay. So we take 5, 7. Oops, we need to be now at hexadecimal mode. 57 FF minus 4000. Okay, that's 17 FF. Okay, Let's try dividing that by 768, and we get 3. So what it's saying is that there are actually 3 areas of the screen, and I'll show you what that actually means. Okay, I've got some notes here that I made earlier, so as I can get this correct. Let's erase what we've got. And this is all relevant because we're going to have a bit of an adventure and try to figure out. We're going to run our emulation. We're going to let it stabilize, and then we're going to stop the emulation. Going to dump out the screen memory, and we're going to see if we can find a character on the screen. Remember that we can't see anything at the moment. The emulation it hasn't anything visible. It's all just kind of running in memory. But we're going to have because we've got memory mapped screen, we should be able to look at the screen memory and see if we can work out if there's actually a character being displayed that we recognise. And if there is, we're going to be reasonably confident that that ROM that we've got is actually executing and is producing output which we'll be able to visualise later on through whatever technique we come up with to visualise it. Okay, so now obviously when we look at a memory address, the screen 4000 to 57FF, then that's made up of 2 bytes, so it's a 16-bit word. Have a look at what actually makes up that address. So let's just list out the bits. 15, 14. 8, 7, 6, 5, 4, 3, 2, 1, and 0. So that's our memory address. Those are the bits of the memory address. Now, because of the area of memory we're dealing with, then the highest order 3 bits are fixed. So this is going to be a 0. This is going to be a 1. This is going to be a 0. Okay, so that's kind of guaranteed. Put a line through there now. So this is because we're dealing with that particular area of memory. Okay, so the next two bits here indicate which third of the screen we're in. What they've done is divided the screen into three sections. Each of them is going to be 7 rows. Is that right? 8 rows. 8 rows long. So we've got the top third will be 8 rows. The middle third will be 8 rows. Bottom row with third rows. That makes 24 lines. So 8 plus 8 plus 8 equals 4. And that's the number of rows or lines on our screen. So for example, if we have, I don't know, 1 0 in there, 0, then that's the bottom third of the screen. If it was 0 0, it would be the top third, and if it was 1 01, it would be the middle third of the screen that we're dealing with. Okay, so the next 3 bits, these here, these represent the line of the pixel. So this is the pixel line. So a character is going to be made up of an 8x8 block. So 8 across here and 8 down here. So as you can see, this goes from 0 to 7, which is 8 different possible values. And so this is row 0, line 0, line 1, all the way down to line 7. Okay. So what that means is that we've got 8 by 8, 64 different cells within here, which can be either a 1 or a 0. So that's going to kind of paint our character. Okay, the next three bits are the line within the third. So we've got 8 lines within the third. So there's 8 possible values in here. It's from 0 to 7, and this is the line. So if we said, for example, on the third, if this was 1 0 and this was 0 0 0, it would be the first line of the bottom third of the screen. I hope you're following. There'll be questions afterwards. And then finally, the last 5 last 5 bits here are the character. Okay. So we've got a pixel line. Okay, so this is the pixel line, and these are the bits which are switched on and off on that line. Okay, let's kind of bear this in mind, and let's run our sample program. See what we see. So I've run this program, and I know that there is output in that memory location, but what I haven't done, and it's been 2 weeks, I've been dying to do this but I haven't done it, is to actually see what that output actually means by using that address pattern there, try and decode what is being output on the screen. And if it's garbage, we know that it's all gone horribly wrong and we're not actually outputting anything intelligible, and that the emulation isn't running the ROM correctly. But if we do recognise what's been put on the screen, then we're kind of more confident and we're onto a bit of a winner. So let's run the sample. So I'll build. And we will open a command line. What should we run? Let's open that. Okay. So we want to go to the bin directory. I can increase the size of the screen for you. Oops. Hopefully you can see that. Debug. Net. There we are. So there's the sample. So we will run sample. Oh, here it runs. So we've already done. We started off this location. Well, it ran to that location. It's done an output. It's output the character, the value 7 to this location, and that's actually, I know what that's doing. That's actually turning the border of the screen black. And now it's running through. So you can see it's not actually advancing past this 1E, the 11E something. And looking at the oh, it's just moved on. So what it was doing there was doing a memory test. It went through all 64K of memory and made sure it was all good. Obviously, it's emulated memory, so it's always going to be okay. Now it's kind of stuck here. It's going as far as 15E, something like that. And if I look at the memory map and the ROM index, this is actually waiting for input. So we're actually in editor mode. As far as I can tell, we're in edit mode, waiting for basic input. And so we should be able to type here. Obviously, we've got no way of interacting with this. So I'm going to press the escape key, and we've just dumped out memory. So we've dumped out the screen memory from 4000 all the way up to 57FF, which is over here. And you can see there is stuff here, which is interesting. So we need a way now of actually interpreting what these values are. So we know that we've got, well, there's something on the bottom row of the screen here. So this is, we're at the end of the memory, so this must be towards the bottom end of the screen. So let's think now. This here will be the very last line. Okay, so this is the very last line that's been written. So let's have a look at what this memory location actually decodes to. So this is 57E0. Let's bring up our handy calculator here. Let's make this a bit, make it bigger for you. You can see it. There we go. So 57E0. 57E0. So this is the pattern of bits here. So I'm just going to move that across onto the screen, and what we're going to do is we're going to write down what that pattern of bits was. Okay, so I'm going to start at the bottom, which is the very last pixel line in theory. So that was 010. So that's the first, that's kind of fixed first three bits. 1 0 1 1 1 1 1 1 0 0 0 0 0 0 0. Okay. So we know what this is. This is just the standard beginning of screen memory. So now the next thing is the third of the screen we're in. And you can see it's 1 0. So this is the bottom third. And we know we're in the bottom third because we're right at the end of memory, of the screen memory. So bottom third. Okay. The next bit is 1 1 1. So what's pixel line? That's pixel line 7. This is a 7. Line 7 of the pixel of our kind of our sprite. So the row of pixels on the very bottom row of our 8x8 sprite. Then we've got the line. The line once again is line 7. And we know we've figured that out. We're on the very bottom row of the screen, and then we've got a bunch of zeros at the end, haven't we? I think I've written too many zeros. Anyway, it doesn't really matter. There's 1 0 too many there. Let's get rid of it. There we go. So there's the last group of. Let's just check this. 010 10 111 111. Yeah, I thought so. What? Still too many. So this is the kind of the end of the. This is what it called the char. We can ignore that for now. So what value is that? Let's go and have a look at our output from our emulator. So that is 3C. See there. Okay, that's 3C. So what we need to now look at pixel row 6, don't we? So everything's going to stay the same, except we're going to be changing the pixel row, which is this one here. So what we want to look at next is 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 0, 0. Let's have a look at what memory location that is. We'll just use our calculator here. We'll put it into binary mode. So we want 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 0, 0. And that's 5, 6, E0. So we've got a pattern now. So this is 5, this one over here, this was 5, 7, E0. This now is 5, 6, E0. And that's going to have a value, hopefully, if we've got any decent output. Let's go and see what's in that location. 5, 6, E0 has got 4, 2 in it. There, can you see that? That's 4, 2. So all that's changing, this one character, this is the first character, this is character 0, okay, first character on the line. The very bottom row of pixels is represented by a byte 30, and the next row up is 42. And we can see that all that's going to change is we're going to step through this group of bits here is what's changing. So the next one we're going to want to have be 1, 0, 0. Sorry, 1, 0, 1. And then 1, 0, 0, and then 0, 1, 1. Let's scroll up a bit. And then we want 0, 1, 0, 0, 0, 1, and 0, 0, 0. So that's going to be, because we're changing this bit, and here you can see we changed this by 1, we decreased this by 1, and our address went from 57 to 56. This is going to be 5, 5, E0, 5, 5, 5. It's right. 5, 4, E0. 5, 3, E0, 5, 2, E0, 5, 1, E0, and 5, 0, E0. 1, 2, 3, 4, 5, 6, 7, 8. That's the 8 rows of our sprite pixel rows. So let's figure out what these values are then. So we'll go up to the next one, which is going to be 5, 5, E0. The 5, 5, E0 is 9, 9. We've got 9, 9 here. And then we've got 5, 4, E0 is A1. Then 5, 3, E0 A1. 5, 2, E0 2E0 is 9, 9 again. So it's already looking promising. We've got the fairly limited set of numbers here. 5100, 51E0, sorry, is 42. And then we've got 50E0. 0E0 is 3C. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 rows, 8 bytes, which represent the pattern of pixels on each of those rows of the sprite. So now we need to figure out, if we can, what that actually means. So let's write down here. I'll just make a note of these values. 3C, 42, 99, A1, A1, 99, 42, and 3C. Okay. So let's write down. We need to write down the binary pattern, the bit pattern. But what I'm going to do, I think what I will do is I'll draw a square. So the presence of a square will be a 1, and the absence of a square will be a 0. So let's get an 8x8 grid of squares for the start, shall we? So let's, oops. How do I do it? What's the best way of doing it? Can we do a copy? Copy and paste. Be more familiar with this tool, really. Come on, copy and paste. Oh, let's try and draw them by hand. I guess don't seem to have any choice. We should be able to copy. Anyone know OneNote enough to do a copy? Let's draw. Select objects. So objects. Not see. There we go. Yeah. That's 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 of them. And let's now copy that block. 1, 2, 3, 4, 5, 6. Control C. Control V. Put that there. C. Okay. There. And then we'll copy the whole lot. Alright. So, hopefully, if we start to write out the bit patterns, with the 1s being a square and 0s being absence of a square, if everything's going to work out how we want it to do, then we should have pattern. And let's see if there is a pattern, then let's see if we can work out what it's supposed to be. Okay, so the first row is 3C. So let's put X in there, 3C, and that is basically it's 0, 0 and 0, 0 at the end with 1s in the middle. So if we get rid of this, these two, and these two. Oops. So that's the kind of first row of the sprite. 4 boxes in a row. Okay, fair enough. Then we've got 4, 2. Let's have a look at 4, 2. 4, 2. So that's, oh, this is looking interesting. So it's zeros in the middle and just ones towards the end. So this goes, and this goes. So it's always kind of starting to think maybe it is some kind of character, and then the middle 4 go. So it could be a 0, couldn't it? What do you think it is, guys? Is it a 0? What is it? And then we've got 9, 9. Getting exciting because that looks like it's going to draw a character. So I'm feeling good. So these two go, and what else was there? These two here. So that's interesting. Okay, now the next 2 rows are A1. Oh, it's interesting. So that's 1. So this one goes. The next one stays, and then the next 4 go. Oops, next 4 go. Okay. And the next one's the same to A1. A1s. What are those? I'm starting to suspect what it is. Anyone else got a suspicion about what it might be? The next one is 9, 9 again. 9, 9 was this row here. It's a copy of that. So this goes. These two go. And these two go. Anyone guess yet? I think I know what it is. And then we've got 4, 2, which is a copy of this row here. Yeah. And then we've got 3C, which is a copy of this row. So, that looks like a copyright symbol to me. If that's a copyright symbol, I think we've actually got a character on the screen. So let's go and let's do a quick search. Let's go and find on here Spectrum 48K boot screen. Let's image. See if we can see someone's got a picture of a Spectrum. Let's boot it up. Oh, look at this! Look at this! This is a Spectrum emulator, but that doesn't matter. It's got a copyright as the first symbol. Remember, there's a border around here, which is why it looks like it's indented. But the very first character is a copyright, and it's got then it should have a set of numbers afterwards. Time Path, welcome to the stream. Good to see you. Have a salute to welcome you. And a hype. Good to see you. Thanks for joining the stream. So it looks like we've got a copyright symbol there. Is there anything else from a real? I'm not sure what that is. So this looks like possibly a real one. 1982 Sinclair Research Limited. So if we could be bothered, we could probably go through that last line of the screen memory that we've dumped, and we should then find that we've got that in the text. So 1980 something Sinclair Research Limited. But there's definitely loads of characters there, and we've definitely got a copyright character at the first. So I'm pretty confident our ROM is running correctly, and we actually painted the screen. You do notice it's pretty much blank. The screen was completely blank apart from the bottom row, and this is pretty much what we saw. If we look at the top third of the screen, up here in the 4000 hex, they're all zeros at the top here, as you can see. So this is an empty screen, and then it starts here at 51E0, which is the the very last line. There's actually a 3C there. No, that's the very last line. That's the top, isn't it? So 50E0 was the start of the last line of the screen. Everything above that is blank. So it's a blank screen apart from the first character being a copyright and then text after that. I have a link to the encoding of the pixels. So I worked out what the encoding of the memory address was from a YouTube video which I watched, where he went through the memory map. So I'd already worked that bit out. I can try and find the link for you if you wish, but I haven't got one. Oh, so the time path. You hear when I was putting the squares on and removing them. So what that is. So what we've done, we've run our Z80 emulator, and we're running Spectrum ZX Spectrum 48K ROM. I'll let it run for about a minute so it's stabilised, and I dumped out the video memory. So this bunch of zeros here represents the area of memory that we're emulating, which represents the screen, what would be output by the Spectrum. The Spectrum, if I don't know if you know what a ZX Spectrum 48K is, it's an old 8-bit kind of games computer from the 1980s. And we're emulating the CPU, which that and many other very popular retro computers actually used to run. The Z80 processor. Yes, rubber keys. Absolutely, rubber keys. It's quite an interesting little machine. I never had one. I did play with them, but yes, it was like calculator keys, rubber things. So it was only about the size of a hardback book, a bit thinner than an average hardback book, but about the size, maybe a little bit bigger than a hardback book. And you plugged it into your TV, and then you plugged a tape cassette player into it, and you could load programs from cassette tape and run basic programs, and a whole bunch of games that you could buy on tape. So we're kind of emulating that at the moment, or we've got an emulation of the CPU, and we're running the ROM, the read-only memory chip, out of that. And we're running that because it's a very simple architecture. The ZX Spectrum is very, very simple. It's 64K of memory, and it was basically made up of two chips. There was obviously this ancillary kind of support chips on there. There's the CPU and something called the ULA, which handled the screen and also handled keyboard input and joystick input and whatever, and sound. Did all that kind of stuff on basically one chip with a set of kind of support chips around it. So it's a very simple architecture. So I'm learning how to do emulation. So we start off with something simple, then we can work up to more complicated machines if the interest continues. So we might have bank switching of memory and start having 512K of memory being addressed by a CPU that can only physically address 64K. Use bank switching and all kinds of techniques for that, and ROM switching. So what we've managed to do, we've looked at what the program actually put into our simulated memory, and those squares that are kind of writing up and removing represent the very first character on the last line of the screen, and you can see here it's that symbol, which is a copyright, and basically I'm so pleased to find that's exactly what those memory locations actually represent. So there'll be a 1 next, a 9, probably an 8, and then I'm not sure exactly what year my ROM is from, but somewhere in the 1980s, and then there'll be hopefully Sinclair. But I'm not going to obviously go through that, because once we've had the kind of excitement, well, I think it's quite exciting, of managing to see that we actually really have got a character, then I can pretty much take it for granted that the rest of the characters will be there. But the thing we're going to do, not tonight, because I need to figure out how to do it. We've managed to use the addresses to work out which character on the line we're printing, which pixel in the sprite, the 8x8 sprite, needs to be on or off, and which third of the screen we're in. So we should be able to loop through that memory that we've got, that we dumped out, and literally draw pixels on the screen and set them to on or off. And the thing I've got that I want to try and use, because what I don't want to have to do is write some kind of emulation which is going to write to the screen 50 times a second and refresh it and handle keyboard input and joystick input and all that kind of stuff. It seems like that's kind of pretty pointless to write that. That's not what we're trying to do. What we're trying to do is provide a Z80 emulator which we can package up as a NuGet package and stick it up on NuGet, and then anyone can download that and do what they want with it. They can build their own emulations. They've got a kind of rock solid emulated CPU. So what I've been looking around, and there's a friend of the stream, Javid X9, also known as One Lone Coder, who does a lot of C++ work, and he wrote a Pixel game engine. And I found that a guy called Chrome Dev or Dev Chrome has actually translated that over to C#, which is the programming languages we're using. And so what I've done is I've forked that repo. So here's my my GitHub. I will remind you that you're free to use any of the code that's in the GitHub. It's all open source, it's all under the MIT license. We've got this pixel engine here. It's from Dev Chrome. So I forked that repo. It uses OpenGL, and it's all written in C++. There's a little bit of sorry, it's written in C#. There's a little bit of C++ in there, and I think we can probably use this to actually provide a screen and also handle keyboard inputs. There'll be a little fiddling with the keyboard because we have to map it to a keyboard matrix that the ROM can understand. But it seems to me we should be able to use this. Now it seems that it's relatively straightforward in terms of we just need to have a class which inherits from game, and then we need to provide a start as a construct, and then we need to actually override the onUpdate. And this is, I think, this is going to be automatically called 50 times a second. So hopefully this should allow us, once I work out how to actually use it, to actually see what's on the screen. Maybe even when we get the keyboard working, to actually start typing a basic program. So Pure7 says still better keyboard than the Butterfly MacBook. That's the new Mac, is it? The Mac Pro. It's a pretty awful keyboard on the ZX Spectrum. I did have a go on one, and because each key was multifunction, you'd have to have a whole kind of combinations of other keys to get the graphics characters to come up and all that kind of thing. It's very fiddly, and they're tiny little keys as well. Which is why I'm interested in the ZX Spectrum Next, which is kind of an update of the Spectrum, which is supposed to be coming out. It's on Kickstarter. That's got a full keyboard on it, and I've also ordered the Commodore 64 clone, which came out just before Christmas. I'm hoping that's going to arrive sometime within the next 4 weeks, and that's got a full keyboard on it as well. So I don't want to fiddle with Spectrum rubber keys. So I'm hoping that this is going to help us. Now there's some documentation on Javid X9's GitHub, but I'm still not exactly sure how to use it. So there's a bit of fiddling to be done, and we'll look at this on a future stream. Maybe actually I might actually just dive in on a stream and see what we can work out how it works. The idea will be that in our sample program here, we'll simply replace this with something which is going to inherit from game and then try and figure out how we can get it to interpret the video memory and map that to pixels or sprites on the Pixel game engine. And I may have to kind of try and get JavidX9 himself to I don't suppose he'll appear on the stream, but maybe give me a bit of advice how to do that. Say I've not even. Well, he's actually got some videos out of when he wrote the Pixel game engine, but I'll probably watch those first, and then maybe if I'm still stuck, just contact him, reach out to him, and ask him to help. Because it should be relatively straightforward once we work, because we know how the memory locations work now. We should be able to write some loops which will go through and update the screen. The fact is, it's got to run 50 times a second, so it could be that in C# it's not quite fast enough. My machine's a bit of a beast, so it might be okay on my machine. We'll have to wait and see. What we've got to remember is that the original Spectrum would be running at about 2 to 4 megahertz, and we've got I don't know 3 gigahertz machine here. So if we're playing games on it, it's going to be running far too fast. But that's not the initial. The initial goal isn't to run games on the emulation, it's just to prove we've got a good emulation, and maybe have a bit of fun writing a basic program or something like that, because that ROM has the full basic programming language in there, including editor, and so it should be a bit of fun. Okay, so with I think that's I'm really kind of pleased with that. I was a bit kind of worried that it wouldn't actually produce any output, or that the output would be a load of garbage, but I'm gratified that it isn't. Okay, so well, let's get a bit of programming. We haven't done any programming yet. We're an hour and a half into the stream and haven't written any code. So let's write some code. What I'd like to do is the remaining kind of a group of instructions that we need to code are this input-output group. And what I've done so far is I've written four bits of code for this group. We've got in A. So what this is going to do, it's going to read a port, a peripheral port, port N, and it's going to load whatever byte is at that location into the accumulator A. So FuelSnable, you're saying the new Mac has reverted to the scissor keyboard, so now it's all good again. Okay, there's even a physical escape key. What an innovation, yes. So, writable bitmap. Yes, I have thought about writable bitmap. I think it may be too slow. It might not, as you point out, it could work. What I'm worried about is going a bit too much into the guts of writing to screens and reading keyboards when that's not really the object. I mean, we may have to do it in the end. If I can utilise that Pixel game engine, which has got all that code written, and that guy's written that C# library there, which uses OpenGL, it'll save me an awful lot of time for something I'm not that interested in writing. However, if it doesn't work, then I shall be coming to you, FuelSnable, to help me out with WPF and writable bitmaps, because I did do a little bit of digging around that, because I've been scratching my head about how we're going to visualize anything out of this emulation, and I did come across that, and it looked interesting, but I'm not sure about like refreshing the screen every 50 times a second, all that kind of stuff. It seems a bit involved. If someone's got a process or program that's already doing that for it, I'd rather leverage that. But yeah, we may come to that. So this is reading a port N and loading the result. Well, it's read out of that port. The port is a peripheral device of some kind. It's reading it out, reading it in, and here we're doing this opposite. We're writing out to that peripheral the contents of the accumulator. Now it's very interesting. If we go back to the memory map spectrum here, I'm going to start. You can see one of the first things it does an out here. It outs to the port FE, the value of 7, which is what's in the accumulator, and it says here make the border white in colour. It said black before, it's actually white. So this port here, FE, is actually this thing called the ULA, and in fact every even value of port is the ULA. So port 2 is the ULA, port 4 is the ULA, port 6 is the ULA, port 8 is the ULA. However, they do recommend you use the proper value, which is FE. This makes it kind of easy really, because there's only one peripheral. It's the ULA. If you've got an even port number, you're writing or reading from the ULA. If it's anything else, it's an error. There isn't another device connected to the Spectrum. So this is why the Spectrum makes a really good kind of starting point. There's lots of complexities. The Spectrum 48K is really simple in terms of its architecture, so maybe we can get our heads around it. The complexity of the ULA chip is that it handles everything: sound, it handles keyboard input, and it handles graphics. So it's a multifunction device. So that's where the complexity comes in, which is why we're going to take it a step at a time. We're going to try and get it so it displays the screen, and if that works, what we'll see is a blank screen, apart from the bottom line where it have copyright 1982, whatever, Sinclair Research Limited, and we'll count that as a victory. And then we'll try and get some keyboard input, and we'll see if we can make the screen change so that as we type, the letters appear. As I say, input and output, any even numbered port is going to be the ULA. However, this code here is not tied to the Z80, so the ZX Spectrum at all. This is completely generic code. So this is the code within a CPU, and if you implement the Z80 in a different machine, then the port numbers will be completely different, and what peripherals are listening on those ports will be completely different. Although we've been looking at spectrums today, spectra, is that the plural of spectrum? Many ZX spectra. Then what we're writing in terms of code is not spectrum specific. It's just an implementation of the CPU instruction set in a ZX Spectrum is what I've said. Okay, then we've got here we're going to take we read in to a register R, so it could be register A, B, C, D, E, H or L, and we're going to read in from a port and write out to a port. Port here is represented by C, and C is the contents of the C register. So if you haven't been following the series on the emulation project, we have a whole bunch of registers within the Z80 CPU. A, B, C, D, E, H and L are the ones, and there's also shadow versions of those, which are not normally accessible. We can utilise in our programs. And here we're saying that we'll have previously loaded register C with the port number we want to write to. In this case, read from, and we're going to read into a register. Okay, so let's have a look at what other instructions we need to write. We've got 125 tests which currently not implemented, so this should be quite interesting to see how many we can get get done. What's the time? We've got half an hour before I'd like to finish. Let's see how far we can get. So let's have a look at the documentation. So this is the Z80 CPU user manual, which lists all the instructions, all the documented instructions. Now we're actually, in our emulation, we're doing undocumented instructions and undocumented features, so that it's a completely accurate, as far as we can make it, implementation of the processor. So any bugs that are in the processor, we're going to emulate the bugs, and any undocumented features, which, you know, in 2020 have been documented because people have spent quite a lot of time figuring out what the undocumented features are and documenting them. So we call them undocumented, but we do know most of them are. There's been quite a lot of detective work actually gone on to figure out what some of these undocumented features of the CPU are. So we've already done in A and in R, C, and we've done. Oh, we haven't done in E. Okay, so we need to do in E. So let's have a look. So what this is going to do, INI. The opcode is EDA2, so it's one of these multi-byte opcodes. It has no operand, so there's no. We're not feeding any values into it. It's the whole process, the whole instruction is encompassed in these 2 bytes. So it says the contents of register C are placed on the bottom half of the address bus to select the I/O device from one of 256 possible ports. Register B can use as a byte counter, and its contents are placed on the top half of the address bus. Then 1 byte from the selected port is placed on the data bus and written to the CPU. The contents of the HL register pair are then placed on the address bus, and the input byte is written to the corresponding memory location. Finally, the byte counter is decremented and register pair HL is incremented. And then these are the flags and the status flags which are updated. So as an example, C contains 07 hex, B contains 10 hex. The HL register pair contains 100 hex, 1000 hex, and byte B7B is available at the push port. Upon execution of INI, memory location 1000, we'll say, hex contains 7B, which is read from the port. HL register is incremented, and the B register is decremented. Okay, so I'll just move that off screen, and let's put some code. So this is going to be, copy this. So this is going to be INI, and it says that memory location pointed to by HL is going to have the value from the port pointed to by register C loaded into it, and then B is going to be decremented, and HL is going to be incremented. So that's the operation. Flags affected. So what flags are affected? Let's have a look. So most of our kind of work in terms of writing this code is actually make sure the flags get set properly. Now it's interesting, it's got unknown values, so we're going to need to figure out that. So flags affected. Let's move that off screen so that I can see it. Okay, we're going to put S as a register, even though it says unknown. The Z register, Z register, H, P, N. C is not affected. The carry flag is not affected according to this. This is going to be INI. Okay. because we're going to be changing flags, we need to set our mythical register queue rather than resetting it. Okay, so we're bringing something in, so we're going to read from, I think, what we need to do. So it says the contents of the registry are placed on the bottom half of the register of the address bus, and register B is placed on the top. So if we look at a standard in, we're going to do this. We're going to read a byte from port BC. That's basically what we're going to do, and then we're going to store that in the location that's pointed to by register HL. Then we're going to say write to bus n HL. So that's kind of the meat of the contain the byte. Oh right, I've got it the wrong way around, that's why. That's it. Write to bus. So we're going to write to memory location pointed to by HL. We're going to write the byte n we've read from the port that's pointed to by BC. And then we're going to increment BC. So we're going to decrement BC. Have I got a decrement? My helpers. Helpers. I got decrement. Increment register pair. There we go. So, where are we? So we want increment HL. The value is going to be right to register pair. What's that? Register pair HL is 2. Okay. So this is going to be the value, which is the value in HL. Register pair 2, and the increment is 1, obviously. We haven't got to include that because it defaults to 1. Then we want to increment the register pair BC, and if we go to our helper, BC is 0, case 0, and our increment is going to be -1. We really decrement it. That basically covers the operation here. Read from the port, write it into memory, increment HL, and then increment BC by -1. Okay, so what we can do now is we can lean on our unit tests to find out what happens next. Okay, so let's I will find that I will find that YouTube link for you. I can't remember exactly where it is, but I can find it. I'm sure I can. Just before I close the stream, I'll try and find it for you. In fact, have I got it squirreled away? Don't think I have. But I will locate it for you. Don't worry, I will find it. Okay, so this, look at our opcodes. Where's the opcodes? Yeah. This is ini, which is an ed command, which is over here. ini is it was on our it was A2, EDA2. There we go. That's what we need to implement. So EDA2. So we can go to our main Z80 class and go and look at the ED instructions table. DD, FD, ED. Here we are. So A2. We can grab this line and duplicate it. A2. Command is ini. It's implied addressing for function ini, and the timing on that is 4534. 534. So these are the T states. It's got 4 machine cycles. The first machine cycle is 4 clock cycles, then 5, and 3, and then 4. And this is where our timing comes in. Eventually we're going to have to work out exactly how to set the timing of each clock cycle so that it's an accurate representation when you run the program. It takes the right amount of time to actually execute a command. Okay, because when you're doing graphical kind of displays and games, the timing is the important thing. And we're nowhere near there yet. Okay. So that's that. So now if I go to our Test Explorer and we run this in debug mode, we should get a failure or a number of failures. So this is our battery of 1300 tests. We got 4 failures. So there's 4 tests just for this one command. I'll post it in Discord, yeah, if you're stable. Having a new quarter at work. You're in a new quarter at work and you're having a lot more work, and you thought, let's see what AI Dungeon has to say about it. Oh, AI Dungeon sounded fantastic. I love the story that you've written about me. You need to hire someone called Marker. It's all going to be good for you. That's really good. I liked how I turned into the Avatar Cthulhu and destroyed all the Martians. It was very interesting, epic as you say. Okay, so let's have a look at what failed. Okay, so there's 4 tests, each got multiple failures. So here it says the accumulator and the flag register expected 145 and got 289. BC. Well, interesting that BC is wrong, isn't it? I wonder why BC is wrong. Wouldn't have expected that, or did you decrement it? And mem pointer. Okay, is expecting to have the value that, a value here. Okay, well, let's see what we need to do. Okay, so let's have a look at our code again. IO. Okay, so it's hard to figure out why BC should be wrong, because we simply decremented the value in BC. Okay, right. So this is reading something in an increment. So one would assume that something very similar to what the flags are happening here are what we require. So let's have a look at the documentation again, and it says that it doesn't know what S is going to be set to. Z is set B minus 1 is 0, otherwise it's reset. H is unknown, that's unknown, that's unknown. D is not affected. Okay, fair enough. So let's look at Z first then. So when we decrement BC, we then want to read register B. I'm going to say if B is 0 after the decrement, then we want to set flag flag Z, the 0 true, else we're going to reset it. And by reset we simply mean set it to false. So what I'm going to do, I'm going to take the rest of these values and we're going to try those. And I think what I'll do at the same time is go and look at our undocumented, the data undocumented. Not what I wanted, not what I wanted. This one here. Okay, this is the undocumented Z80 documented, and we want to go to the section on undocumented flags. And let's whiz down undocumented effects. Our instructions. Okay. There's the outs. It's bizarre. It says these are the most bizarre as far as the flags are concerned. INI uses the C register instead of the L register. There's a catch though, because not the value of C is used but C plus 1. So there's a catch though, because not the value of C is used but C plus 1 if it's INI, or C minus 1 . This says it does set the carry flag, you see. It's interesting, isn't it? Okay, it says the H flag and the C flag are going to be set if the contents of HL contents of C plus 1 and 255 is greater than 255. Okay, interesting. I'll just move that out of the way. So that's saying the H flag. Well, let's what I'm going to do is I'm going to run this with that code that we just copied down, because I think it's not going to be right, but let's see what effect it has, because it is very bizarre. Yeah, so it's expecting 397 in those two registers, and it's got 415. Let's see if we can sort that out to begin with. I don't know how much more we're going to get done tonight now. We might not get this working. So it says that the H flag and the C flag are set. H flag is set if it's not the value of C that's used, it's C plus 1 if it's INI. Okay. So it says if HL plus C 1 we're going to AND that with FF if that is greater than FF. It says that the carry flag is the same. There's the carry flag. Is it the contents of HL? So let's read this a bit clear. Okay. I said this is bizarre. Okay. First of instruction, the following flags. The S, Z, Y and X are affected by decrementing register B as in deck B. Okay, so deck B, an arithmetic operation. We've got a helper here. Set deck flags. So we could run that initially, couldn't we? So what we'll do, we'll run this. So how are we using this? Okay, so we need to run sending the value before being decremented and the value that's been decremented. So in here, try doing this. So the value is the value. We needn't do that. This should take care of it. So we'll need to var val equal B, the var deck val equals B, and then we valid term byte. Oh yes, of course it is. Okay, so that should set that up. Now, documentation specifically says that the N flag is set, but I think the N flag is set by set deck flags. We go look here. N flag is set to true by that process. What's going to happen is that the Z flag will be set. and so will Y. These two flags will be set as well, as we want them to be the decremented value. Okay, the complications are H, C and P. So this is being set here, but we're going to have to overwrite it the same here. Okay. So we're saying that these are the ones we need to set. We don't need to set those either because they've been set by our deck flags. So the P, this is okay, so it's very similar. Parity, if I just show you this, it's hilarious. So the parity flag is the parity of the result of that calculation. The H plus C plus 1, ANDed with 255, ANDed with 7, then XORed with B. So it's that. Let's do a bar X is going to become that. The parity of X, and then the rest of the command is, it says so they AND the whole lot with 7. Okay. And then exclusive or the whole shooting match value of B. I think exclusive or is that. I want that to be a byte. Where it gets a bit silly with this casting, so let's bar and we'll cast the whole lot as a byte. Parity, what does it want to take? U short. Parity wants a U short. Really? Okay. Brackets, isn't it? Will that do it? Okay, well that's what it reckons it should be. I'm not really convinced. Let's give it a go. So we still know it's going to fail. And it's still got it wrong. So we got 394. So it's time to actually break that down. Let's have a look at what 394. It's expecting 415. So let's have a look what it's expecting. So it's only decimal 415. So it's the last byte that we're interested in. So that's as you can see there, the last byte is 10011111. That's 415. That's what it's expecting. And it got 3. It got 394. 4. Let's put that in. 394. So it got 1000 1010. Okay, so there's three bits there which are not what we wanted. Let's have figure out what bits they are. Not this. If we go to our Z80 class and just scroll right to the top of this class, we've got our flags register. Okay, so we've got a carry. The first byte, bit 0 is carry. Then we get the N, which is the negative value. P, X, undocumented. Then we get H, an undocumented, which we're calling U, Z, and S. This is the sign flag. So what this is saying is that it expects the carry flag to be set, and we're not setting it. The parity flag to be set, and the half carry flag to be set, and we're not setting any of those three. Which is interesting. So I wonder, rather than HL, if it's actually the contents of HL that we're supposed to be testing. So rather than HL here, if this is N, is the contents of the register HL. The contents pointed to by HL. We just read them in here. And then we get C+1 for some reason. And then all those other things. So let's try that and see if that makes any difference. Okay. And we're getting the same value. It's expecting that. We're still not setting those values, those three flags. And I'm running out of time. So let's have a quick look at the old. I might have to leave this, and it's not very satisfying. Let's have another quick gander at this. Take the state of the L after the increment, decrement of HL. Add the value value written to the item. Well, that K for now. If K is greater than 255, then the F and H flags are set. State of L after the increment. And the value written to the IO port. So this is, it says for INR we use C rather than L. So the state of that register after the increment or decrement, we've done that. It says we use C+1 if it's INI or INIR. Okay, so we've got that. The content for this HL here is the value that we read out of HL, the memory location pointed to by HL. So that is N there. So let's grab this here. Put that into there. Okay, so if we stick a breakpoint here and run that again, the Y is 28, which is not greater than 255. N was 154. Ah. I think that's the problem. Let's try that. This here, that's Y there, isn't it? See what that does. Do 8. 28. N is 154. C plus 1 is 131. Which is certainly greater than 255, but we're adding it with that. This documentation is quite hard to really. So it looks like we're adding that's being added together there, isn't it? Let's try writing this again. Okay, so we've got brackets there. We've got N plus brackets C plus 1 brackets ampersand. Make sure we write that correctly. It looks like it's actually this. Try again. Trying it again. Yeah, I'm running out of time here, guys. Let's just run it through. Still failing at that point. Still got plenty of failures, but you can see we're not actually managed to affect that value. Still getting 394. 394. Daniel Loudon, welcome to the stream. Good to see you. Yeah, we're kind of struggling a bit here with this, setting these flags. As it gets more weird, and so this is the most bizarre set of instructions, the input-output instructions. It's really important we get them right. It looks like we've got everything right, so this is all correct. It's just these three flags here, P, C and H, which aren't being set. When everything says it should be. The test wants them to be set, those three flags, and they're not being set. I'm just going to write the function exactly as it's written here and see if it looks any different from what I've got. I'm just going to move this across the screen for send. So it's saying bracket HL plus bracket D1 and 255. Greater than 255. And this here is N. That is what we've got here. It doesn't add up with the number of brackets in the instructions. 1 2 1 1 3 4 3 2 1. It doesn't close all the brackets. Assuming it must be there. Try one more. Oh, we got some result there. We got 411. Oh, that's better. So 411. So we actually made it change. So let's pursue that. So clear this 411. That means we've now got the carry flag is now set, and the half carry flag is set. So it's just the parity flag which isn't being set now. That's 411. So that's good. We're getting there. So 411. Okay, so we just need to set the parity flag now. So let's go and look at the parity flag. So now we're saying that's Y ANDed with the value 7 and then exclusive ORed with B. I think that is exclusive OR. So they're saying it is exactly the same as this value of y, and remove these brackets from. Y ANDed with a value of 7 exclusive OR with B. I'm pretty sure that's exclusive OR. Yes, exclusive OR. So we'll take the parity of that. So the parity of the parity now is it even or odd parity? Is there an even number of ones or an odd number of ones? So we're saying the parity of the value y that we've got there ANDed with 7 and then exclusive ORed with B. Now I wonder if that value of B is before or after decrement. Let's have a look. So let's bring this across again. It says if we take the value, we take the out version, which uses H and L. PFS is like set like the parity of K bitwise ANDed with 7, bitwise ORed with B. Parity of K, and we could call this K if we wanted to, couldn't we? Let's call it K, so it's consistent with the documentation we use. And then they're saying it's K, parity of K, like the parity of K, bitwise ANDed with 7, bitwise exclusive ORed with the value of B. Is that B pre or post declaration? So let's see if it's rather than B, let's set it to val, is the value before it was decremented, and see if that makes any difference. Look. Now we can pop a breakpoint there. So let's run through that. That says the parity is false. Not going to set it, and we want it to set it. So let's set the decremented value through, shall we? Decval. Try that. False. Oh, it's sending a 0 through there, look. That's why. We're not sending the right value in. Okay, I'm sure we should be able to sort that out. X. Let's remove that. Comment that out for a second. Let's run it again. It's a casting, we're not casting correctly, that's the problem. Interesting. Why didn't it hit where we wanted to hit? Why wasn't it hitting that? Okay, let's try again. We don't want to do that. Here we are. So this is 158. 158. Have a look at that. 158. 158. 1, 2, 3, 4, 5, 6. That's 5, which is odd parity. 158. If we pass val into there. Yeah, this is kind of the story of writing this program, really. It's 158 still. That's 4. Have we got anything else in the way of documentation? Let's have a look at this. Flags affected as in decrement B. N flag is copied bit 7 last value. Take region C, add 1 to it. If the instruction increases HL, otherwise decrease it by 1. Okay. Now add this value to the IO port. Carry the carry of this last addition is copied to C and H. Beats me that the test show this to be true. We've got C and H working. It's the parity flag that we're struggling with. So you can see this is like weird stuff. I might have to stop at this point. I don't think I'm going to solve this very on stream. So this I need to cast it to a short and sign short. This is what it's saying, isn't it? K is that value there, ANDed with a value of 7, and then exclusive ORed with B, which is either val or dec val. I would assume it's dec val, to be honest with you. Time, it's 25 past 10. I'm going to have to stop, I'm afraid, guys. Hello there, Emuk. It's good to see you. Thank you for joining. And PSF, thank you as well. Good to see you. Sorry, I've been kind of absorbed in this problem. We've got everything kind of on this initial pass through the failing tests of sorting out the status flags from the CPU. Everything's now correct apart from the parity flag, which is this P here. Thank you very much for the follow. That's really kind of you. So I have some electric alf hype. It's really annoying. I mean, we're not going to get the whole of all of the tests passing because there's things like mem. Let's see if we can sort out mem pointer while we're here. So mem pointer is like another weird feature. should be a bit easier to sort out. It's INI, mem pointer is equal to BC before decremented plus 1. BC before decrementing B plus 1. So this is going to, so mem pointer, so we can say mem pointer equals increment just a pair BC. How do I do increment? We just want the value of BC plus 1. That to a U short. That's that one. Let's see if that improves our. It will still have 4 failures, but maybe we'll have less failures or fewer failures within each individual test. The mem pointer is like an artificial register. It's not a real register, or at least not known to be a real register, but it is something which affects the values that come back. So we've decreased the number of failures. We had 3 failures here. Now we've got 2, 2, and 1. Okay, so we've got that's sorted something out. Let's see what else is. So this is interesting that BC. So that could be the problem, that BC is actually got the wrong value in it. So we're obviously using the value of B, aren't we? I just wonder how that could possibly be a problem. We've got BC here. Shall we do BC minus 1? Just a bit of coding, and then we'll assign to register and to register pair. Not for register pairs. Right to register pair. And the destination is 0, and the value is C minus 1. Cast as a U short. Try again. Yeah, still got the same problem. BC expected 39298, got 39553. How all we've done is decremented it. How can that possibly be the case? Oh, this is interesting. So let's stick a thing there. Yeah, I can't leave this go, but I'm going to have to in a second. I'm sticking on. The BC contains 39554. Well, that's not consistent with what the test is expecting. That's completely consistent with what we're actually doing. So we decrement. So that's what we've just done. We've decremented by 1. So we've got 39553 or 2. Do that. In this last one, it's just B that's wrong, and it's grossly wrong, isn't it? Completely different value. Right, I'm gonna have to think about that. I think I don't think I haven't got time to do that now. So thank you everyone for joining me. It's been an interesting stream. I haven't got anywhere near doing what I wanted to do, but hopefully we can sort this out on the next stream and get it working. We're into the really weird commands now. So once we've got this one working, we'll have the formulae for the input and output and the increment decrement versions of this. This is the increment version. There's a decrement version as well. And these are used for kind of reading to whole tables of input output, so we can scan through a whole bunch of values and write them in off the peripheral and write them into memory, into contiguous memory locations. That's what this is all about. As you kind of tweak what INI and INI are, which is the next one we then have to do, and the out versions. That's what they're there for block reading of values. So I'm sorry that we're going to have to end without resolving that issue, but there's just too many failing tests there, and not enough time for me to look at. Already gone about half an hour over where I wanted to stop. So just to remind you that all the code that we write, apart from I shan't be pushing this yet, but all the code we write is on GitHub. It's all under the MIT open source license, and this is the location of my GitHub. So you're perfectly welcome to go and look at the code, take it, do it whether you want. There's no need to kind of give attribution or anything like that. There's all kinds of stuff on there. My chatbot is up there. It's quite a complicated chatbot. It runs across Discord, Slack, and on Twitch chat. It's got most of a full-blown old-school text adventure in there. Lots of other commands. There is there's a synthesizer written in WPF. There's Alexa skills. There's a Microsoft bot framework stuff up there. There's Mesh Sharp work we did with FuelSnable on parsers and parser combinators. There's a whole bunch of stuff. There's about 35 kind of repositories up there. Go and check it out. And my YouTube channel, which this video will be archived to, is here. I've just reached 180 subscribers on YouTube. If you do feel generous, they're completely free to subscribe on YouTube, but if you head over there and just hit the subscribe button, they really help me out. Thank you for those people who followed today, and for those people who subscribed. That's been really, really kind of you. And I'll either see you Wednesday afternoon if kind of real life allows me to, or it'll be next Monday. We'll continue with this project. Also, I need to speak to FuelSnable about doing some more shader streams, pixel shaders. So if you're interested in pixel shaders, there's a whole bunch of videos up on the YouTube channel. Really, we're developing 2D and 3D shaders from scratch. An example of one of the ones that we created is this one, which is this. You'll see it come up in a minute. Which is Alpha, our alien buddy, being launched into space, and all of that is being generated in real time. Apart from Alf, the rocket plume there is real time generation, as are things like our hype here, which is stuff. Yes, and FuelSnable has done some fantastic stuff over Christmas. There's one really, really impressive kind of Doctor Who like shade, 3D fractal shader, and some other stuff incoming raid. So thank you very much for joining me. I shan't push this code up to GitHub because it's basically broken at the moment, but I will work on it, and I'll see you either, if real life permits, see you on Wednesday afternoon around about 4 o'clock UTC. Failing that, it'll be next Monday again, from approximately 7:30 to 8, somewhere in that kind of time range, and we'll hack some more code on here, and hopefully once we get this one working, the rest of it should be a lot easier, and we'll finish off the last of the opcodes and be in a good position to carry on with trying to get the Spectrum emulator to actually produce a picture. So thanks once again, and let's go and find someone to raid, shall we? So let's pop over to here. This is a new screen. I was going to move you off. Move this off screen. So we want to raid channel. So who should we shade? Source Scoot. Bald bearded builder. Let's try raiding the bald bearded builder, which is quite hard to say. So do join me next time, and stay on the channel if you'd like to join the raid. So take care everyone, and I'll see you again soon. Who's just about to raid me? Oh dear. Never mind. We'll forget that. So, thanks. Yeah, make the other guy merge. Okay. Well, I'll take care, anyone, and I'll see you again soon.